bond polarity, whether bonds are polar or not. And this turns out to be really important. And it's actually where electronegativity comes in. This applies to covalent bonds only. Okay? And it's due to differences in electronegativity. En for short. And that is a reminder, that's how tightly the outer shell electrons are held to the nucleus. So if you remember, way back when, before the exam, I talked about when we diagnosed atoms, we worked out nitrogen, oxygen, carbon, all those things. Figured out how many bonds they could make, and that was now clear why that's important for the structures we've been talking about. But then also I talked about how electronegative they were, and I had said, look, I'm going to deliver on a promise that I can tell you why it's useful in a little bit. And today's the day where I can show you why it's useful. And so some reminders and some simplifications. So electronegativity, we will not worry about numerical values. In chemistry, they will make you know more about this. But basically, we're going to make some broad categories: very low, medium, high, and very high. All right. Very low are things like sodium and potassium. I'm sorry, not with a plus, but sodium and potassium. Things in the middle are carbon, sulfur, hydrogen, phosphorus. Oxygen and nitrogen have high electronegativity, and things like chlorine and fluorine have very high electronegativity. For the most part, this is relevant to Bio 111. And so you might ask, what happens when two atoms form a covalent bond? And there are three possibilities. And so, like I said, there's three cases. Number one, if the electronegativities are roughly equal, that's one possibility. Two, if the electronegativities are different, say medium and high. And three, if they're very different, say high and low. Or, I'm sorry, I should do it this way. Very high and low. All right? So there's three cases. And I'll draw them one by one. So if they're roughly equal, the electrons are shared equally. And I'll show you what this means in just a second. Therefore, the bond is non-polar covalent. And let me show you, for example. If you have a carbon and a hydrogen, which both have medium electronegativities, their two electrons are going to spend most of their time in the middle. We draw that, it's just a plain C-H bond. And the electron cloud is in the center. So why does electronegativity matter here? If you remember, it's the degree to which the nucleus pulls on those outer shell electrons. How tightly does it hold on? Carbon and hydrogen are about the same. So, you know, if the man in the front right shirt, no, you're not Matt, you're Andrew, sorry. Andrew in the red shirt in the front row. He's a carbon atom and I'm a hydrogen atom. We both pull on those electrons equally. Those electrons hang out mostly in the middle, right? So that the bond is not polar. There's nothing special about that. We share the electrons equally because we pull on them equally hard. That's relatively uninteresting. Things get a little more interesting if they're different. If the electrons are shared, electronegativities are different unequally. If the electronegativities are different. The electrons are shared unequally, and the bond is polar covalent. All right, it's called polar now. And the idea is there, a classic example would be oxygen and hydrogen. Oxygen has a high electronegativity, and hydrogen has a medium electronegativity. And so the electrons are going to spend more of their time around the oxygen because it pulls them more tightly. And so you would write this thing as O-H, but you write them with this little delta. Let me write this very clearly because it's a funny little Greek letter. Delta plus, and delta minus. These are what are called partial charges, here and here. And the electrons are closer to the atom with higher electronegativity. All right? So let me explain what I mean by that. So again, if Andrew and I are bonding, right, we're sharing a pair of electrons. Suppose he's oxygen. He pulls on those electrons much more hard, with much greater strength, because it's kernel charge and a variety of other things than I do. So those electrons, he's a stronger positive force than I am. So those negative electrons are going to spend more time over by him. We're still bonded. It's still a covalent bond. We're still sharing, but it's not equal anymore. He's pulling harder on his end, and I'm not pulling as hard. So the electrons spend more time over by him. What does that mean? It means I've, on balance, lost a fraction of electron. So I'm not +1, like I lost a whole electron, but I'm, plus 0.01, a slight imbalance. And he's like a minus 0.01, because on balance, the seesaw is tipped, and the electrons are spending more time over by him. So his atom has a delta, and that's a Greek letter delta. That means a little itty-bitty bit, like a hundredth, or a few hundredths, or maybe a tenth at the most. So this isn't a full +1. The electron hasn't been fully taken away from the hydrogen, but it's not being shared equally. So the electrons spend less time here. So this is sort of net slightly positive, and that is net slightly negative. Right? And so that bond is now polar. It's not equally shared. There's a plus and minus charge. And we'll see that turns out to, there's interesting consequences of that, which we'll see in a minute. All right. Just to sort of fill out the spectrum, if the electronegativities are very different, electrons are taken by the high electronegativity atom. And that leads to an ionic bond. And that is, you end up with something like this. Say in the case of chlorine, it's actually got the 2 electrons just around it, and the sodium has no electrons around it. And this is really Cl minus and Na plus. All right. It turns out these are not seen in Bio 111, but they're there for reference. So this is sort of extreme. On this end, chlorine is so electronegative, it actually steals an electron from sodium, and this gets a full negative charge. And sodium is a full positive charge. If you work it out, sodium lost 1 electron should be positive, and chlorine gained an electron should be negative. In the middle, you have unequal sharing. They're pulling on it, tug of war. In the tug of war, oxygen's winning that tug of war, not completely, but enough to be slightly negative. So not a full minus charge, but like minus 0.01 or something like that. And then here, everybody's happy. The seesaw is balanced. The tug of war is totally neutral. The electrons, there's no net charge on that bond. Everybody's sharing happily. Right? And that's why electronegativity is important, because it tells you whether a bond is going to be polar or not. And later on, it'll be, this distinction here will be really important for a variety of things, which I'll start to tell you soon. Before we get there, questions about this spectrum, charge theft, that sort of thing? Yeah? Yes, so it's hard. What I should probably do is different colors. Well, you know what? Let me do it this way. That thing is oxygen, and around it is its cloud of electrons. Those are 2 electrons, the 2 electrons, and they're some of the time near the hydrogen, but they're more of the time near the oxygen. Is what I'm trying to say. Okay, so why is the oxygen inside? Because the answer is, so Andrew's got, so if he's the oxygen and I'm the hydrogen, the electrons are going to be spending more time on him, not only just between us, but also on the other side of him. They're sort of surrounding him more to give him, that's what gives him that negative charge. The electrons spend more, well, he's pulling on them harder, so they spend more time near him, including sometimes on the other side of him from me. That's what I mean by this. So they're surrounding him now. Other questions? Yeah. So the third possibility is just the extreme of the second. If Andrew was chlorine and I was sodium, he's so electronegative, he just actually takes the electron away from me. We don't share at all. There's not a covalent bond anymore. It's actually an ionic bond.